Alright, let's get started. We begin today's class with this question on electrophilic addition reaction. Please make sure you write out the carbocation to figure out the answer to this question. Now you can pause the lecture here while you're working on the answer to this question. Alright, let's take a look at this question. Find the major product of the reaction. You're given this alkene and HCl as the other reactant. First step is to identify what is the nucleophile and what is the electrophile. Alkenes, we know, behave as good nucleophiles. HCl you can write as H plus and Cl minus. H plus is the electrophile in the reaction. The first step in an electrophilic addition reaction is attack of the pi bond by the electrophile. So draw the arrow from the pi bond towards the electrophile. I'm going to add the H plus to this carbon of the double bond. The reason being, only if you add the H plus to that carbon, there's a chance to upgrade the stability of the carbocation. If you add the H plus to this carbon, you will see that there's no way you can upgrade the stability of the carbocation. And as we learned in the last lecture, the reaction will take the path of the most stable intermediate. And that is why I'm going to add the hydrogen to this carbon of the double bond. So let's write the product. There is already a hydrogen there. I'm adding a H plus. You're forming a new bond. As a result of that, you get a positive charge on that carbon. So that is the carbocation you have formed. Now if you take a look at that carbocation, it is a secondary carbocation because the carbon bearing positive charge is attached to two other carbons. And as we learned in the last lecture, the secondary carbocation is not the most stable. The tertiary carbocation is the most stable. So if there is a pathway to upgrade the stability of this carbocation, the reaction will take that path. And as we have learned from the last lecture, there are two ways to upgrade the stability of a carbocation, a 1,2 methyl shift or a 1,2 hydride shift. So let's take a look at this structure now. If you take a look at this carbon that's adjacent to the carbon bearing positive charge, you have a hydrogen. So I can move that hydrogen as a 1,2 hydride shift. All right. But if I move that hydrogen, I will result in a secondary carbocation again. So there will be no change in the stability of the carbocation. So there's no point of moving any of these hydrogens. All right. Let's take a look at the other carbon attached to the carbon bearing positive charge, this carbon. That carbon has methyl groups. Now if one of those methyl groups moves as a 1,2 methyl shift, the resulting carbocation will be tertiary, which is more stable. Therefore the reaction will take that path. You will have a 1,2 methyl shift resulting in a tertiary carbocation. So the metal has moved here to this position. The hydrogens are there as it is. There's no change there. And as a result of the metal shift, you have the positive charge on that carbon. Now if you take a look at the nature of this carbocation, it's a tertiary carbocation. The carbon bearing positive charge is attached to three other carbons. That is the most stable carbocation, so the reaction will take that path. And if this now reacts with Cl minus, which is the nucleophile in the second step, this is the electrophile, the carbocation, the product you will get is option C. Right. So the major product of this reaction would be option C. All right. So whenever you're writing the product of an electrophilic addition reaction, write the carbocation and check if there is a chance to upgrade the stability of the carbocation through a 1,2 methyl shift or a 1,2 hydride shift. If there is a chance, the reaction will take that path. All right. The next chapter we begin in this semester is chapter 8, Alkenes, Reactions and Synthesis. In this chapter, we're going to take a look at a lot more reactions of alkenes and also take into account the stereochemistry of the product. Now, one thing I would like to mention at the beginning of this chapter is please don't memorize the reactions. It will become very difficult for you. Try to understand how the reactions are taking place and based on that, write the product. All right. The key idea of this chapter is that alkenes undergo electrophilic addition reactions and the planarity of the carbon-carbon bond allows attack of the electrophile from the top or the bottom face with equal probability. Right? You'll understand what this statement means as we take some examples. Right? So let's begin by taking a look at the dihalogenation reaction of alkenes. Some key points about dihalogenation. It is the addition of X2. X stands for halogens. Across C double bond C. The resulting products are 1,2 dihalides and the reaction occurs with anti-stereochemistry, which is an anti-addition of the halogens. Right? So let's understand these statements with the help of an example. So let's say I have this alkene. The reagents for dihalogenation are the halogen. I'm taking the example of bromine. You can take iodine or chlorine. All right. The solvent usually is CH2Cl2. Now sometimes the solvent will be mentioned, sometimes it will not be mentioned. Right. But the active reagent in this reaction is the halogen X2. All right. Now the product, when I say anti-addition, it means one bromine is up at one of the double bonded carbon, the other bromine is down. Anti means opposite side. So you have anti-additions of the halogen. You are adding bromine to each of the double bonded carbon. Anti-addition means one bromine will be up, one bromine will be down. All right. Now you have a metal in the reactant here that will still be there. The metal will be up because the bromine is down, the metal will be up. But the relationship between the two halogens will be anti. Okay. So the stereochemistry will be anti in dihalogenation. Always keep that in mind. All right. Now the reason these are called 1,2 dihalides is if I call this carbon 1, it has a halogen. The second halogen is on carbon number 2. Right? So the relative positions of the carbons bearing the halogens is 1 and 2. Therefore, you call them 1,2 dihalides, the product. All right? So let's take a look. Why does this reaction result in an anti-stereochemistry? Now, please pay close attention to the mechanism of this reaction. You'll have similar mechanisms as we move along in this chapter. I'm going to use the document camera and the model simultaneously to show you how we form this anti-product. All right. So here are the two reactants in the reaction, the alkene and the halogen. Each bromine atom has 3 lone pairs. All right. The first step is to identify the nucleophile and the electrophile. We already know alkenes behave as good nucleophiles. All right. Now the bromine molecule in the presence of alkene can split up heterolytically. So these bonded electrons can go towards one of the bromine. As a result of that, you will form Br plus and Br minus. Br minus has 4 lone pairs. Br plus has 3 lone pairs. So the electrophile in this reaction is Br plus. Now the way I'm writing the mechanism for this reaction is a very simplified way. It is not the most accurate way, but it will work for us to understand this reaction. All right. Now that we have identified the nucleophile and electrophile, the first step in electrophilic addition reaction, attack of the pi bond by the electrophile. So let's write the product of that. It's a symmetrical alkene. You can put the bromine on the top or bottom, it doesn't matter. So let's say I put the bromine on the top. This bromine has 3 lone pairs. As a result of that, you have a carbocation that is formed. That's the intermediate in an electrophilic addition reaction. First step always results in a carbocation. Now watch very carefully what happens now. Bromine donates one of its lone pair to this carbon bearing a positive charge. As a result of that, what you form is called the cyclic bromonium ion. Cyclic bromonium ion. All right. Now you can form the cyclic bromonium ion at the top or at the bottom. Okay. Bromine still has two lone pairs. Bromine with two lone pairs, two bonds, is a formal positive charge. Right? So you can form the cyclic bromonium ion either at the top or at the bottom. Let me explain you that with the help of the model. All right. So to begin with, this is your alkene. All right. So these two are the sp2 hybridized carbons. As you can see, they are in the plane of the paper, trigonal planar, bond angle 120 degrees. All these are sp3 hybridized carbons. Right? All of these four are sp3. These two are the sp2 hybridized carbons having the double bond. I'm not showing you hydrogens for clarity. Now, because a double bond is planar, it's in one plane, when the bromonium ion comes, Br plus comes, it can come from the top or from the bottom of this double bond with equal probability. Right? Because this double bond is flat. So the attack can happen from the top or from the bottom with equal probability. If it happens from the top, you get the bromonium ion on the top. Okay? If it happens at the bottom, you'll get it from the bottom. All right. And there is equal probability, which means if you start with 100 molecules of this, you will get 50 molecules of this, 50 molecules of this. All right. So let me show you the structure of cyclic bromonium ion. So here is the top cyclic bromonium ion. As you can see, the Br plus ring is on the top. The hydrogens are at the bottom. Don't forget there are hydrogens here. They are at the bottom. All right. Similarly, you can have a cyclic bromonium ion at the bottom. The hydrogens will be on the top for that. Okay. And please keep in mind the reason for these two forming with equal probability is because of the reactant. The double bond is planar, so the attack can happen with equal probability from the top or from the bottom. All right. So this is your top cyclic bromonium ion. The red is the bromine. You can see the three-membered ring on the top, hydrogens at the bottom. Right. So the first step in this reaction is formation of the cyclic bromonium ion. Okay. All of this happens in one step. As I said, I've simplified it to you and written it stepwise. But all of this happens one step. All right. So this is step number 1, formation of cyclic bromonium ion. Okay. Now once this is formed, you also have Br minus floating around. Right. Now the Br minus will attack from the opposite side of the ring. Right. So this bromonium ion, the Br plus ring is on the top. So the Br minus will come at the bottom. For this bromonium ion, the Br plus ring is at the bottom. So from the top, the Br minus will come. From top, from bottom. Okay. So again, let me show you that with the help of the model. So here is your top bromonium ion. As you can see, the ring is on the top, hydrogens are at the bottom. Now the Br minus cannot come from the top because this ring is blocking it to approach. It has to come from the bottom. All right. So if the Br ring is on the top, okay, the approach of the Br minus has to be from the bottom. If the Br ring is at the bottom, like here, the Br minus will come from the top. Right? So let's write the products once the Br minus reacts with the bromonium ion. So let's first take the Br minus approaching from the bottom to this ring. So Br minus is coming from the bottom, it's attacking this carbon. These electrons will go towards the Br plus. So at this site, the attack is not taking place. Br will remain up at this site. Hydrogen there at the bottom. Right? Now Br here is coming from the bottom to this carbon. So Br there will be at the bottom. And hydrogen will go to the top. Right? So where the bromine is coming, to whichever carbon it's coming from the bottom, at that carbon you'll have the bromine down because it's coming from the bottom. At this carbon, the reaction is not taking place with Br minus. So there Br was up, it will remain up. Okay? And both the Br now have 3 lone pairs. The electrons for this bond that is formed between carbon and bromine is coming from the minus charge of the Br. Alright. So this is one molecule you will form if the reaction takes place from bottom with this ring. Let's now write the product for this one. Okay. The reaction here, Br minus is coming from top, it's attacking that carbon. Right. So this carbon is remaining untouched, so let's write it there as it is. Br there at the bottom. Hydrogen on the top. Right. So as Br minus comes here, these electrons will go to the Br plus. So it becomes neutral. Now it has 3 lone pairs. Right. Br minus is coming from top at that carbon. So at that side you'll have Br top, which means hydrogen is at the bottom. Okay. Again, this bromine also has 3 lone pairs. So as a result of this reaction, you form this product and this product. Let me show you those two products clearly on a paper. So these are the two products formed in the reaction. Now if you take a look at the relationship between these two products, these two are enantiomers. As you can see, the framework of the molecule in both are the same. The bold bromine became a dotted bromine. The dotted bromine became a bold bromine. So at every single chiral center, you have opposite configuration in both these molecules. Therefore, both of these are enantiomers. And keep in mind, you're going to form equal amounts of these. You're going to form 50% of this molecule and 50% of this molecule. Right? Now, a mixture of product containing equal amounts of both the enantiomers is called a racemic mixture. So this reaction is going to result in a racemic mixture because you're forming equal amounts of the enantiomers. Right? And keep in mind, a racemic mixture will behave achiral because it has equal amounts of the enantiomers. All right? So let me show you these two compounds with the help of the model. So this is this compound. As you can see, bromine up, bromine up. At this carbon, bromine down, bromine down. All right. Let's take a look at this compound. Bromine down, bromine down. This carbon, bromine up, bromine up. Right. Now, as you can see, these two are enantiomers. There's no way I can superimpose these two. However way I try, they're non-superimposable mirror images. Right. These groups are not matching. You can try any way, they will not match. All right. So this reaction results in enantiomers in equal quantities, and enantiomers in equal quantities is racemic mixture. And keep in mind, this is happening because of equal probability of the electrophile attacking the double bond. All right. So let's write this mechanism again in the slides. So the reactants in the reaction are alkene and Br2. Alkene is the nucleophile. Br2, we said, in the presence of the alkene is going to break heterolytically to Br plus and Br minus. Br plus is the electrophile in the reaction. Right. First step, attack of the double bond by the electrophile. Now because the double bond is planar, you can have the Br plus attack from the top or the bottom with equal probability. If it attacks from top, you're going to form this cyclic bromonium ion. If it attacks from bottom, you're going to form this cyclic bromonium ion. The Br minus that is floating around will attack from the bottom to a cyclic bromonium ion that's on the top. This is on the top, so this attack will be from bottom. It's attacking this carbon. The electrons in this bond will go to Br plus. Okay. So this site, the attack is not taking place. So that site will remain as it is, Br up there. Right? This site, the attack is not taking place. The attack is taking place here from the bottom. So where the attack is taking place, there the bromine will be at the bottom, because there it is coming from the bottom. All right. Now for this bromonium ion, the Br minus will come from top, because the bromonium ion is at the bottom. All right. Now the attack is taking place here. Br minus there is at the top. It is coming from the top, so there it will be top. The attack is not taking place here, so there the Br will be down. Right. So these are the two products you will form in equal amounts. These two are enantiomers. And you will form 50% of this and 50% of this. Right. And 50% enantiomer mixture is called a racemic mixture. A racemic mixture behaves achiral. Always keep that in mind. All right. Let's take another example. Let's say I'm starting with this alkene and I'm performing dihalogenation with Br2 and CH2Cl2 as the solvent. Always dihalogenation reaction, bromine will be added anti to the double bonded carbons. All right. So if Br is up, Br will be down at this carbon. You can also form with equal probability Br down here, Br up here. Right. Now you'll form 50% of both these products. The only chiral carbon in both these molecules is this. This is the chiral carbon. This is a CH2. Okay, it's not chiral. All right. So you'll form 50% each of both the enantiomers, which means you'll end up with a racemic mixture. Right. Now, when you are dealing with straight chain compounds, not rings like the previous example, you can just write the product as this. You don't need to show stereochemistry. You don't need to show the anti, one bromine up, one bromine down. You don't need to show that. Just write it like this. The reason being, even though this molecule is formed anti, one bromine up, one bromine down, it doesn't remain anti because this is a carbon-carbon single bond. They can freely rotate. All right. So let me show you what I mean by that with the help of the model. All right. So this is the reaction we just discussed on the slides. Let me take this molecule, for example. So here is the structure of this molecule. This carbon is this carbon. As you can see, bromine is at the back. In my perspective, bromine is in the back. Hydrogen is in the front. So you have a hydrogen here in the front, right? And the hydrogen is in the front, bromine is at the back. This carbon, which is your chiral carbon, has bromine in the front coming towards me, hydrogen at the back. Right? And then you have a CH2, CH3. I have not shown you hydrogens. Right? Now this molecule, when it is formed, it will form anti due to the mechanism we discussed in the previous slide. So if you look at the Newman projection, you can see that these two Br groups are anti. One up, one down, 180 degrees angle and tie, all right? But it need not remain like this because these two bonds can rotate. It's a carbon-carbon single bond, right? So even though it's formed anti, it need not remain anti. That is why when I'm dealing with a straight chain compound, I can just write the product normally like this, right? Br and Br with normal bonds because they're not going to remain anti, right? But keep in mind, you will get a racemic mixture. Okay? You're going to get a racemic mixture. Okay. On the other hand, when you're dealing with a cyclic compound, you have to write the Br's opposite, anti, one up, one down, right? Because when you're dealing with a cyclic compound, you can't rotate, right? You're stuck with the ring. So in a cyclic compound, make sure you show the stereochemistry. One bromine up, one bromine down, all right? In an acyclic compound, a straight chain compound, you can just write the product like this. So let's take a few more examples on dihalogenation. Let's say I'm starting off with this compound. This time I'm using chlorine as the halogen. Again, the focus of the reaction is the double bond. Don't worry about the rest of the molecule. It's just going to tag along, right? It's a straight chain compound. So you don't need to use bold and dotted. Just write the chlorines to each of the double bonded carbon. All right. Now, as you can see, you are forming two chiral centers as a result of this reaction. All right. And you will get a racemic mixture. Keep that in mind. You'll get equal amounts of both the enantiomers. All right. Let's take another example. This is a ring compound, so you have to show bold and dotted, right? Again, you're going to get a racemic mixture. So if I put the Br up here, the Br should be down here, and tie. If the Br is up there, the methyl group is down, right? So that is one enantiomer. The other enantiomer will have Br down here and Br up here. The methyl will be up now here, right? Again, you'll get 50% each of this, which means you will get a racemic mixture. Now, one thing I want to point out about dihalogenation is you don't need to worry about Markovnikov rule here because the reagent is symmetric. You are adding the same atoms to both the double bonded carbons. If you take this example, you are adding Br to both the double bonded carbons. So you don't need to consider Markovnikov rule for dihalogenation. All right. So here is a question for you on dihalogenation. You can pause the lecture here to answer this question. All right, let's take a look at this question. What is the relationship between the expected products of the reaction below? So you're performing a dihalogenation reaction with this alkene and chlorine as the halogen. So let's write the products. If I put the chlorine up here, the chlorine will be down here, which means the methyl will be up. The second product I can form is chlorine down here, chlorine up here, which means the methyl will be down. Right? Now I know I said a couple of slides back, for a straight chain compound, you don't need to draw dotted and bold, right? But when the question is on finding the relationship, write it out like this, dotted and bold. That will allow you to see the relationship. If I give you this reaction and ask you to draw the product, then just draw normal bonds. Don't put bold and dotted. But when the question is on relationship, write it like this so that you can see what is the relationship between the products. All right. Now, if you take a look at both these products, this carbon is not chiral. you have two CH3s. Right? So these carbons are not chiral. The only chiral carbon in both these molecules is this carbon. Okay. And this chiral carbon is formed as a result of this reaction. To begin with, that carbon was sp2, it was not chiral. Due to this reaction, you have generated that chiral center. And there is equal probability at that chiral center to have chlorine up or chlorine down. Right? So these two are enantiomers. You're going to generate them 50% each, equal probability. Overall, the compound mixture will be racemic. All right? But the relationship between the two is enantiomers. All right? So please write out the products when you're asked a question on relationship. Check if they're enantiomers or any other relationship. All right? That finishes dihalogenation. The next reaction is formation of halohydrins from alkenes. It is the addition of HOX to the double bond. Halohydrin. Halo stands for halogen. Hydrin stands for OH. So essentially you're adding OH to one of the double bonded carbon, halogen to the other double bonded carbon. So let's look at some features of this reaction. It is the addition of HOX across carbon-carbon double bond. It's an anti-addition of OH and X. Like your dihalogenation, it is an anti-addition. All right? And always OH is added to the more substituted carbon of the double bond. Halogen is added to the less substituted carbon of the double bond. All right? So let's take an example. Let's say I have this alkene. The reaction conditions for halohydrin is halogen and water. Right? Halogen goes to the less substituted carbon of the double bond. OH goes to the more substituted carbon of the double bond. Right? So let's write the product. It's an anti-addition. Right? So if I put OH up here, the Br should be down here. The methyl group will be down here because OH is up. Right? That is one product you'll form. The other product will be its enantiomer. OH down here, which means methyl will be up, and Br would be up. You're going to form equal amounts of both these enantiomers, which means you'll end up with a racemic mixture. All right. So let's now take a look at the mechanism for this reaction. The mechanism is very similar to dihalogenation. Right? Let's begin by drawing the reactants in this reaction, the alkene and the halogen, Br2. Each bromine has 3 lone pairs. Now the first step in the mechanism is exactly same as dihalogenation, formation of the cyclic bromonium ion. Br2 in the presence of alkene will split up into Br plus and Br minus. Alkene will behave as the nucleophile, Br plus will behave as the electrophile. You can form the cyclic bromonium ion on the top or at the bottom with equal probability. Again, I'm not showing you all the arrows. We have just discussed that a couple of slides back. All right. So the first step is exactly the same, formation of the cyclic bromonium ion. Let's put in the methyl group that is there on the reactant. If Br is up here, methyl is down. If Br is down here, methyl group is up at that carbon. The second step in this reaction involves opening up of the cyclic bromonium ion with the help of water. Please keep in mind this reaction has two reagents, bromine and water. Bromine is involved in the first step of the reaction, water is involved in the second step. And always water will go to the carbon that is more substituted. right? So this carbon is more substituted of the double bond. That is where water will go. All right. The reason being that carbon that is more substituted can handle positive charge better. So that's where the water will go. All right. So in the second step, water is behaving as the nucleophile. That carbon that is more substituted is behaving as the electrophile. And as we have learned with dihalogenation, if the cyclic bromonium ion is on the top, water will go from bottom. Right. So let's write the product. Water is going from bottom here, so there you'll have OH at the bottom. That's the carbon where the reaction is taking place. So OH there will be at bottom because water is going from the bottom. OH2 plus. Metal group will be pushed to the top. In that process, these electrons will go to Br plus. It will become Br neutral. And this carbon, the reaction is not taking place there. There the Br is up, it will remain up. So the Br is going to remain up. All right. The reaction is not taking place at that carbon. Right. The final step, you have plenty of water floating around. Water can act as a base. It can pluck this proton, give the bonded electrons of this bond to oxygen to make it neutral. OH, Br, and you'll generate some H3O plus. This water will take up that proton to give H3O plus. Now you can ask me the question, why is Br minus that is generated in the first step not opening the Br plus ring? Why is Br minus not behaving as the nucleophile in the second step, but water is behaving as the nucleophile? The reason being, water, also nucleophilic, is the solvent in this reaction. And usually solvent is present in large amount compared to reagents. Therefore, there is a vast excess of water compared to Br minus. That is why predominantly that will behave as the nucleophile in the second step. There's a lot more water than Br minus. All right. So let's also write the product from this cyclic bromonium ion. Water is the nucleophile. This carbon is the electrophile. Because the bromonium ion is at the bottom, water will go from top. So at that carbon where the reaction is taking place, you'll have water at the top. Oxygen with 3 bonds, 1 lone pair, formal positive charge. Right. Now because water is on the top, the metal group will be pushed to the bottom. Right. Now as water attacks that carbon, the electrons in this bond will go towards the bromine, Br plus. And it will become Br neutral. So here Br will remain down. At this carbon, the reaction is not taking place. So however the Br is there attached, it will remain like that. Br will be down there. Right. Final step, react with water, where water is behaving as the base. It's going to pluck the proton. The electrons in this bond will go to oxygen, and the oxygen will become neutral. Now as you can see, these two products are enantiomers. At every single chiral center, they have opposite configuration. And you're going to form equal amounts of both of these enantiomers, so you're going to result in a racemic mixture. All right. So as you can see, this reaction mechanism is exactly same as dihalogenation. First step, formation of the cyclic bromonium ion. The second step, again opening that cyclic bromonium ion with the help of the nucleophile. The only difference between dihalogenation and halohydrin is the nucleophile in the second step is different. There the nucleophile was Br minus. Here the nucleophile in the second step is water. But the mechanism is exactly the same. You will form enantiomers in equal quantity, therefore it will be a racemic mixture. Alright. So key points about the halohydrin reaction. It is the addition of OH and halogen anti to the double bonded carbons. Always OH will go to the more substituted carbon of the double bond, halogen to the less substituted carbon of the double bond. Alright. So let's write a few more examples on this reaction. Let's say I start off with this alkene. The reactants, halogen and water. Halogen to the less substituted carbon, OH to the more substituted carbon. Now, because this is a straight chain compound, like in dihalogenation, I don't need to show the product with bold and dotted. Because even though they're formed that way, anti, the bonds can rotate, single bonds, and they don't remain anti. So I can just show normal bonds. Alright. Now, in this reaction, you're going to get only one product. No enantiomers are going to be formed in this reaction because there is no chiral carbon in the product. This carbon is not chiral because these two are the same groups. This again is a CH2. So there are no chiral carbons here. All you're going to get is one product in this reaction. You will get enantiomers only when you're making chiral carbons. Keep that in mind. All right. Let's take another example. Halogen goes to the less substituted carbon. OH goes to the more substituted carbon. Now this is a ring compound, so you have to show the stereochemistry. You can form the halogen up here, which means the OH will be down. So this bond would be up then. That is one product you'll form. The other product you'll form is its enantiomer. Halogen down here, OH up, which means this bond is down. Right. You'll form equal amounts of both these enantiomers, so you'll end up with a racemic mixture. Right. So here is a question for you on halohydrin reaction. You can pause the lecture here to answer this question. Alright, let's take a look at this question. What is the relationship between the expected products of the reaction below? As you can see, I'm starting with an alkene. I'm performing a halohydrin reaction with chlorine and water. Right? So the reaction is asking you about relationship. So write the products with the bold and dotted bonds. Halogen goes to this carbon of the double bond. OH goes to this carbon of the double bond. All right. So let's write the products. That part, the reaction is not taking place. So that part will remain as it is. The site of the reaction is this double bond. All right. So I can have the OH up there, which means the chlorine would be down. Anti-addition. That's one product you will form. The other product you will form is OH down and chlorine up. So those are the two products you're going to form in this reaction. So let's now look at what is the relationship between the two. If you take a look at both these products, you have two chiral centers in each of them. At this chiral center, in both the compounds, the configuration is the same. Br is up, hydrogen is the back. They differ at this chiral center. Right? So these two compounds at one chiral center have the same configuration, at the other they differ. So these two are stereomers. right? So if you're starting off with a compound that already has a chiral center, that chiral center is not going to get touched in the reaction. So it's going to remain as it is in both the products you're forming, right? This site that is generated as a result of this reaction, it's going to be enantiomeric at that site, OH up, OH down. But this site is not going to change in both the products, right? So examine the products carefully. These two are diastereomers, all right? Let's now go back to the hydration reaction of alkenes we discussed in chapter 7. Just to remind you, hydration is addition of water, hydrogen to one of the double bonded carbon, OH to the other double bonded carbon, right? And as we have learned, this reaction always follows the Markovnikov's rule. OH goes to the more substituted carbon of the double bond, H plus goes to the less substituted carbon. And if you remember, the reagent we use in this reaction is H3O plus. Water in combination of a strong acid like H2SO4. It's an electrophilic addition reaction. The first step is attack of the double bond by the electrophile H plus, right? So the carbocation you will form as a result of that is this carbocation. So if I draw the arrow, it will start from the nucleophile, which is the alkene, and it will go to the electrophile H plus. And that is where the H plus has gone. And if you look at the nature of this carbocation, it is a tertiary carbocation. Carbon bearing the positive charge is attached to 3 other carbons. It is the most stable carbocation, so you don't need to worry about upgrade in stability. The second step in this reaction is attack of that carbocation by water. Water is the nucleophile, the carbocation is the electrophile. Now if you remember in chapter 7, we also discussed the structure of carbocation. It is a planar molecule, trigonal planar sp2 hybridized. Because it's a planar molecule, the water, when it attacks in the second step, can attack from the top or from the bottom with equal probability. So you're going to get 2 products that are enantiomers. So let's write those products. So let's say water attacks from the top. You have the OH at the top. This bond will be at the bottom. If the water attacks from the bottom, OH will be at the bottom and this bond will be at the top. So you get equal quantities of both these products, and as you can see, both of these are enantiomers, so you will generate equal amounts of both the enantiomers, which means you will get a racemic mixture. So always keep in mind, hydration of an alkene results in a racemic mixture. All right. Let's take another example on hydration. Let's say I'm starting off with this alkene. The reagent for hydration is acidified water. You can always split that up into H plus and water for the sake of simplicity to write the reaction mechanism. All right. Alkene is the nucleophile, H plus is the electrophile. Draw the arrow from the double bond towards the electrophile. H plus goes to the less substituted carbon of the double bond. So that's where the H plus is going to go. As a result of that, you have made a positive charge at that carbon. All right. Now if you take a look at the nature of this carbocation, the carbon bearing positive charge is attached to 2 other carbons. It's a secondary carbocation. So you need to check if that carbocation can upgrade the stability to a tertiary carbocation. And as you can see, you have a hydrogen on that carbon that is adjacent to the carbon bearing double bond. You can have a 1,2 hydride shift. Move the hydrogen there. As a result of that, you're going to form a tertiary carbocation. The carbon bearing positive charge is attached to 3 other carbons. This is the most stable carbocation. Therefore, the reaction is going to take that path. Now, if that carbocation reacts with the nucleophile water, you will get OH at that site. All right. So as you can see, hydration reaction will always be governed by the most stable intermediate that is going to be formed in the reaction. Okay, the reaction will always go through the path of the most stable reaction intermediate. All right. So let's say I want to make a compound starting from this alkene where I want the OH on this carbon. I want to put the OH on this carbon of the double bond. I can't use H3O+, because if I use H3O+, the reaction is going to go through the tertiary carbocation. I'm going to get the OH on this carbon. All right. So how do I put the OH, install an OH on this carbon of the double bond? Okay. In other words, can you prevent carbocation rearrangement? Can I prevent this path of the reaction so that I can put the OH where I want? I want the OH to be on this carbon, so can I put it there? Right? That is where the oxymercuration reaction comes into picture. Oxymercuration is also hydration of alkene. You are adding H and OH to the double bonded carbons. It will always follow the Markovnikov rule. The key difference between this reaction and hydration is that there is no carbocation rearrangement, because the mechanism does not proceed via a carbocation intermediate. So in this reaction, there is no upgrade in stability, there is no 1,2 methyl shift or a 1,2 hydride shift. All you're doing is installing the OH on the more substituted carbon of the double bond, period. All right. So let's look at this reaction and the reagents in this reaction. So I'm starting off with the same alkene in the previous slide. The reagents in this reaction are HgOAc twice, water, that is step 1 of the reaction. The step 2 is NaBH4. Right? If I expand HgOAc, this is how it will look like. So it's mercury bonding to the oxygen that is negatively charged. Okay. This entire thing is called OAC, acetyl. AC stands for acetyl. So this is OAC. All right. NaBH4 is an ionic compound that splits up into Na plus and BH4 minus. It is called sodium borohydride. So this reaction involves 2 steps, right? So when you see step 1 and step 2 on an arrow, it means you're performing the step 1 after the other. So you're taking this alkene in a reaction vessel, putting these reagents first, let the reaction go to form a product, then you're adding the second set of reagents to complete the reaction, right? That's what it means when you see 1 and 2, right? So you need both these steps to complete this reaction. And as I said, in this reaction, you are adding OH to the more substituted carbon of the double bond, H to the less substituted carbon of the double bond. Don't worry about any rearrangement because there is no carbocation intermediate in this reaction, right? So whenever you have this reaction, blindly you can put the OH on the more substituted carbon of the double bond, H to the less substituted carbon of the double bond. Now we are not looking at the detailed mechanism of this reaction. All you want to know about oxymercuration is that it is a hydration reaction and it will always follow the Markovnikov rule. OH to the more substituted carbon of the double bond, H to the less substituted carbon of the double bond. All right. So let's take an example on oxymercuration and hydration combined. In this question, I've given you the product for oxymercuration, and I'm asking you the alkene reactant that will give this product. Right? And as we have learned with oxymercuration, the OH is added to the more substituted carbon of the double bond. It will always follow the Markovnikov's rule, and there is no carbocation rearrangement. So in the product, if you see OH attached to this carbon, it means in the alkene, that carbon was the more substituted carbon of the double bond. Right? So you have to have the double bond between these two carbons. If you have the double bond between this carbon and this carbon like this would become more substituted then. OH will go there upon oxymercuration. So the double bond has to be between these two carbons. So let's write the reactant. CH3, CH3, that has a hydrogen, CH, double bond, CH2. If you take this alkene and perform the oxymercuration, OH will go there because that is the more substituted carbon of the double bond. If you put the double bond here in the alkene reactant, this carbon will become more substituted and OH will get attached there. So that can't give you this product. All right. So the double bond is between these two carbons. All right. Now let's say I give you this alkene and I ask you to write the product if the reagent is H3O+, hydration in the presence of acid. This reaction will go through carbocation. So write out the carbocation that is formed. H3O+, I can write as H+ and water. First step, the double bond is attacked by H+. H+ is going to go to this carbon. You'll form a carbocation here, H+ went there. So CH2 became CH3. All right. As you can see, this is a secondary carbocation. You have a hydrogen here that can move through a 1,2 hydride shift. That will result in a tertiary carbocation. Now if this reacts with water, you will get the OH attached to the tertiary carbon. So as you can see, the same alkene, depending on what conditions you are using, can give you different products. Right? Oxymercuration, always the OH will go to the more substituted carbon of the double bond. No carbocation rearrangement. Hydration through H3O+ is governed by carbocation stability. Right? So you will get the product that goes through the most stable carbocation path. All right. So here is a question for you on hydration. You can pause the lecture here while you answer this question. All right, let's take a look at this question. Which of the following reactions would not result in a 50-50 mixture of stereoisomeric products? Now always keep in mind you will get 50-50 mixture only when you're forming enantiomers. When the relationship between the products you form are enantiomers, that is when you will get 50-50. So this question is asking you when you will not get 50-50, which means you're looking at a scenario where you are not forming enantiomers as products. Right? So let's take a look at both of these reactions. The first reaction is a hydration with H3O+. So it's going to go through carbocation. H+ will go to this carbon of the double bond. You'll form a tertiary carbocation, which is the most stable. So there is no rearrangement there. OH will go here. Now OH in the product can be on the top or at the bottom. So let's write both the products you form. That part of the reaction is not changing, and that carbon is not a chiral carbon. Both of these are CH3s, right? So it's not a chiral carbon. You can form the OH up, which means the metal will be down, or you can also form the second product with equal probability, OH down and the metal group up. Right? You're going to form 50% of this and 50% of this. You're going to form a racemic mixture. So reaction A will give 50% and 50% of both the products. All right. Let's look at the second reaction. You're beginning with this alkene, again reacting with acidified water. So you're performing hydration through carbocation intermediate. H plus will go to this carbon of the double bond. You'll form a tertiary carbocation, which is the most stable, and OH will go there. So let's write the product. Now, as you can see, this product has no chiral carbons. There is a plane of symmetry running here. This carbon is not chiral. Right? This path is same as this path. So in reaction B, you're going to form only one compound. There is no 50-50 mixture because there is no enantiomers. Right? The question is asking you which of the reactions you will not form a 50-50 mixture. So the answer is reaction B. Right? So only when you're forming enantiomers, the answer will be 50-50 mixture. Right? Whenever you're not forming enantiomers, you will not get 50-50. All right? So we'll end today's lecture here. Please go over the mechanisms we have discussed in today's lecture. Let me know if you have any questions. Have a good rest of the day.